It's radioactive. Now, this is a Geiger counter, and what it does is it detects radiation when stuff is given off. So right now, you hear an occasional click. It's picking up background radiation, which is usually of the type of alpha, beta, or gamma. But if I bring it close, it picks up more radiation. And if I remove the lead shielding, it picks up a lot of radiation. So what's happening is there's decay happening right now. And this decay is reduced exponentially with distance. It's called the inverse squared law. Have you ever covered that in physics? And basically what it means is if you have a point source that's giving you a radiation amount, every distance you travel away, the radiation becomes diluted by a factor of a square. And the reason's pretty simple. Okay? So this value here, if I call it D, is 4D here and like 8D here. It's a value of a squared. So that means that over here, the distance between particles has been diluted as you move closer. You won't be asked about any of that. Okay? So what they did was they took this radiation source, they put it near a magnet. They noticed some of the red stuff was not attracted to a magnet, but the black and the blue was. So what they figured out was that the black stuff being attracted to positive must be negative, and they called it beta. The black stuff being attracted to negative must be positive, they called it alpha, and the stuff in the red must not be anything. They determined later on that alpha radiation was nothing but a helium nucleus, which of course, it should be positive, is atomic number -2? No, it's +2, and beta emission is negative. Typo on this. I don't know. The atomic number of this is 2 because it would have 2 protons and 2 neutrons, but no electrons. So you know that helium that filled up your birthday balloon? That used to be alpha radiation. But in the years that have passed, it's picked up the electrons it needs, and now it's a now it's a noble gas. Okay? Beta radiation is this blue stuff. It's nothing but an electron. And gamma radiation is the red stuff. It's just high intensity light. Positron emission and electron capture are kind of details that we're going to go over, but they're kind of tricky. So what happens is nuclear decay reactions are actually quite simple. You see how it's written? One atom becomes 2 particles. 1 becomes 2, 1 becomes 2, 1 becomes 2. There's a reason for that. So in this case, what you notice is you got numbers on top that represent the mass, numbers on bottom that represent the atomic number. These will always add up to that. These will add up to that. Now you're thinking, I thought some of the mass was converted into energy. Well, notice these are rounded off to the nearest whole number. If we went into the decimals, we would find that this side was lighter than this side. These are a little bit heavier. And the missing, I'm sorry, take that back. These are a little bit heavier than this one. And the reason these are a little bit lighter is because when this reaction occurs, some of the mass is converted into energy, and that's why these particles are given off with a great deal of energy. So these energy particles are one of the reasons we have lava underneath our feet. The interior of the Earth is hot for 2 reasons. The gravitational friction of the iron and the alpha decay of uranium-238. There's a lot of that beneath us. This reaction is constantly happening, and the kinetic energy given off warms the Earth's core. Over time, when there's less uranium-238, there'll be less lava, less volcanoes, maybe less earthquakes, I don't know. But you ever see those pictures of the dinosaur movies where it shows the volcano in the background? There used to be more volcanoes because there used to be more uranium-238 and the core of the Earth used to be hotter. So I want you to quickly notice 3 things. Alpha decay always gives off an alpha particle. That means that 238 becomes 234, down by 4, so it gets 4 lighter. And 92 becomes 90, goes down by 2 fewer protons, always. Beta decay always gives off an electron. So this is kind of weird. Notice the mass stays constant, but what happens is the atomic number goes up 1 from 90 to 91 because the beta particle is a -1. Okay. Gamma doesn't make any changes in the numbers. It's where you have a high energy electron that simply gives off its energy in the form of light. Very high energy light though. Positron is a quark. I hope you wouldn't get asked about that. It's like a positive electron. It's technically antimatter, whatever. And electron capture, that's something kind of interesting. We're going to talk about the process of this in just a little bit. But what I want you to do real quickly is I want you to try a couple questions, just to yourself. I want to see if you can, under exercise 19-1A, I want to see if you can do A and B. No, wait, A and alpha means one of those will be the helium nucleus, and then I just do the math. So 212 minus 4 gives me 208 on top. 86 minus 2 gives me 84 on bottom. I look at the periodic table again, and I call that PO polonium. Is that what you got? Okay, so uranium is a chemical that will decay a whole bunch of times. It'll decay by alpha, beta a couple times, alpha about 5 more times, beta, alpha, beta, alpha, beta, alpha. It'll keep doing that until it gets to something that's stable, non-radioactive. Now, why would it decay in the first place? Well, that's because the binding energy between the protons and electrons just isn't quite enough. It's kind of like if you were to build stairs, and instead of using 20 nails, you ran out, so you used 16. You know, it's going to probably fall apart sooner than it should. Not tomorrow, not the day after tomorrow, but one of these days it's going to fall apart because there's just not enough adhesive to hold it together. In the same way, there's not enough nuclear energy to hold the nucleus. So what happens is once in a while you'll have a decay event. And those decay events take different various amounts of time. But you can see that one uranium atom actually could give off like almost 20 radioactive particles before it turns into lead. And lead is the heaviest non-radioactive stable isotope. In our planet, the uranium is getting converted to lead. So when geologists want to know how old that rock is, the way that lava works is lead will sink towards Earth's core and uranium will rise to the top. Fresh rock is almost entirely uranium. What you do is you then analyze the rock by measuring the uranium-lead concentration, and you can determine then basically how old the rock is. Why? Because radioactive decay is first order. First order means we can use half-life concepts on it, and now we're doing kinetics. It's first order decay. So when this happens, remind me again, if it's a rate law that's first order, that means I'll get a straight line when I graph time against what?
Natural log.
Natural log, right. Natural log of its, we wouldn't use concentration, but what you'd do is you'd measure like all those beeps given off, and I could say, ooh, fresh rock would give me 200 decays per minute, according to those beeps. Ooh, my rock gives me off 188 decays per minute. Let's put those two values, thinking of them as concentration, and that gives me an initial and a final that I could use my rate law calculation with. Frankly, I don't think you'll ask to be doing much in the way of rate law, other than to kind of think about kinetics in terms of its particle view, like, oh, hotter particles move faster, increasing the rate of reaction, something like that. But I'm not sure. I don't know. I've never taken the SAT 2. So here we are. They're kind of showing that natural log thing, giving us a straight line. They're also giving us something called various half-lives. So in Algebra 3-4, you discussed half-life, right? And if I said, oh, draw a half-life graph, you'd have a graph that looked like this. And basically, every dot represents half of the dot above it. So that's 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/28, something like that. And in straight line, in natural log form, that'll give us this. So the half-life you're seeing here is determined by these values. Uranium-238 has a 4.5 billion year half-life. So Earth which is 4.5 billion years old, has used up about half of our uranium. So you can tell it's a really long half-life. Now all these other steps that we saw, much shorter than that. So this first step takes about half-life of 4.5 billion years old. All these other steps might take seconds, minutes, hours, or in some cases a few 100,000 years. But if you compare a few 100,000 years to 4.5 billion years, it's a blink of an eye. I don't think you're going to be asked too much beyond this. So the big thing is that you're going to be able to need to write nuclear decay equations. That's the one thing that you're most likely to be hit about. And if you look here, that's kind of what they're hitting on most also. They're kind of showing decay equation after decay equation.
Wait, Mr. Paul,
yeah.
which one's the strong? Which one releases the most energy? Okay.
They're relatively similar. Okay. Here it's going over fission and fusion. That's pretty much what we covered. You guys need to get to class, and we got to get ready for a new class. Can you put this back where you got it from over there?